Okay. All right. Everybody at home, guys, get a thumbs up that you hear me okay? And you guys can see the board okay? Okay. So I've written down, there's different methods you can use to solve these problems. And there's going to be ways in the future when we get to higher degree inequalities that we're going to have to use one method over the other. But right now you have options. Method one, I'm going to do this first because we're going to have to use method one in the future at some point. So we have to know method one. If you want to solve a quadratic inequality using method one, it's called the sign analysis method. First, you have to compare your inequality to zero. So we'll get everything on one side of the inequality compared to zero. All right, then you're going to find the zeros, right? So setting a quadratic equal to zero usually leaves factoring the quadratic formula, something to find those zeros. All right, then you're going to perform a sign analysis, and I'll show you what that is. I'm just giving you guys a chance to write it all down. I got myself ahead by putting it on the board already. The second method, I think, is going to be the method that a lot of people are going to prefer today because it is such an easy method with the quadratics. Using method two, it's using the graph. You're going to compare it to zero. You're going to find the zeros, just like the first method, but instead of using a sign analysis, now you're just going to sketch a graph. Guys, we're working with quadratics right now, which graphs a parabola. Parabolas only do two things as of right now. They either open up or they open down. So it's a really easy sketch, and we know if it opens up or down depending on the leading coefficient A. So the sketch is extremely easy to make, and it gets us a lot of answers very, very quickly. So I think method two for quadratic inequalities is my favorite. Okay, and then the third method, which, yeah, you can use it, and I think it's going to help a lot when we get into higher degree inequalities, but as far as the quadratic, they're not that difficult, so I don't know if you'll have to go through all of these hoops, but it's to each their own. This is when you're going to use the intersection of the two graphs, so you basically don't compare it to zero. You treat the left side of the inequality as one function, and you treat the other side, the right side of the inequality, as a separate function. And then you use the intersection feature. Where do these two graphs intersect? And then you can look at their graphs to see where one graph is greater than the other graph and vice versa. It's nice. You can use your graphing calculator. Desmos does a really nice job because the picture to me is nicer and it's more user-friendly. However, Desmos won't be that great when we have to find the zeros that aren't like reducible, simplifiable, nice x-intercepts or zeros. This one, the graphing calculator will find a more accurate x-intercept for us. But either way, okay? So these are your methods. I'm going to show you the first two methods using this one, and then the second example, I'll show you the third method really quick. But again, I don't think it's necessary with a quadratic inequality to have to use a graph, or the graphing calculator, I should say. All right, so I just want to make sure you guys are good because I got to erase this to move it all up. Are you good? Okay. Are you okay, Michael? Yeah. Everybody home, can I erase this? I got to move it up. Everybody okay at home? Okay. Okay, so here it is. Our job is to solve this inequality. We have to find all of the x values that we could plug in that makes this inequality true. So guys, essentially, you have to find all the x values that when you plug them in and do this PEMDAS, this has to always turn into some number that is less than or equal to zero. So what numbers, what x values are going to turn this expression into some number that is less than or equal to zero, which is a negative number. So what x values turn this into a negative number, basically. All right, well, step one, we're going to use method one first. Method one said compare it to zero. Guys, it's already compared to zero. You have everything on one side compared to zero. So that part is done. Now, step two would be to find the zeros. What numbers actually make this expression equal zero? because those numbers are the boundary numbers between positive and negative outputs. So now we're going to find the zeros. So I don't know about you guys, but I'm going to hope it factors. So now we find the zeros. All right, what multiplies to negative 12? That adds up to negative 4, negative 6, positive 2. Zero product property, set our factors equal to 0. X would have to be 6 here, and X would have to be negative 2. So guys, these are the numbers that physically make this expression equal 0. So plug 6 in, this will become 0. Is 0 less than or equal to 0? Yes. So 6 is an answer to this problem. Plug negative 2 in, it'll make this become 0. Is 0 less than or equal to 0? Yes. So guys, these are answers, but they're not the only answers. There's a lot of other answers that could make this expression a number less than or equal to 0 too. So what you do now using method 1, you use your zeros, these numbers, as your boundaries. So put them on a number line. All right, we got negative 2, and we got 6. We just said that these are the numbers that make it equal 0. So they are solutions. So do you guys remember when you were on a number line and you wanted to show that this number and this number were solutions? What kind of dots did you put at these numbers? Whole dots. Whole dots, close them in, right? So put closed dots to remind yourself that at the end of the day, negative 2 and 6 are answers to this problem. Now guys, if this had just been less than 0, since 6 and negative 2 make it equal 0, I wouldn't want to include them because I would just want to be a number less than 0 but not equal to 0. Then you would put open circles on this line to remind yourself that they're not answers to this problem, okay? All right, so now what these numbers do is they cut your x-axis into thirds. You have this section of x values, you have this section of x values, and then you have this section of x values. The sign analysis says to pick one number from each interval and test it. And you're going to test to see which numbers make the inequality true. I want you guys to know this method because we're going to have to do it in our future. We're going to have to perform sign analysis in our future. All right, so we're going to pick test numbers. We're going to test, guys, what's an easy number to the left of negative 2 that we could plug in and test? Negative 3? All right, so we're going to test negative 3. And it's called a sign analysis because we ultimately don't care what the number is. We just care what the sign of the number is. So guys, if you plug negative 3 into this problem, you can either plug them into the multiplied out form, or it's easier to plug them into the factored form. If you plug negative 3 in, is negative 3 minus 6 going to be a positive or negative number? Anybody know? If you plug negative 3 in, is negative 3 minus 6 a positive or negative number? Negative. Again, we don't care about the number, we care about the sign. It's a sign analysis. All right, if you plug negative 3 in, is negative 3 plus 2 a positive or negative number? Negative. So guys, what's a negative times a negative going to be? Because, right, I would have had a negative number here and a negative number there. What's a negative times a negative? Positive. So is a positive number, which is what you're going to get when you plug negative 3 in, going to be a number that is less than or equal to 0? Is a positive number less than or equal to 0? No. Then guess what? These are bad guys. You do not get answers to this problem for x values on this interval. Cross them out. They don't work. All right, let's pick another test number. Now let's test this interval. Pick a number in between negative 2 and 6 that's really easy to work with. My fave, 0. Okay, now one at a time, let's test 0. So if you plug 0 in, is 0 minus 6 going to be a positive or negative number? Negative. Is 0 plus 2 going to be a positive or negative number? Positive. What's a negative number times a positive number going to be? That's going to be a negative number. Is a negative number going to be less than or equal to 0? Yeah, these are good guys. A negative number will make this true. A negative number will be a number less than or equal to 0. So these are good guys. So we have answers in between negative 2 and 6. All right, and then pick a number out here. What about numbers over here? What's a number we could test to the right of 6? 7. Okay, plug 7 in. Is 7 minus 6 going to be positive or negative? Positive. Is 7 plus 2 going to be positive or negative? Positive. What's a positive times a positive going to be? a positive, is a positive number going to be less than or equal to 0? No. So these are not good answers either. So the only x values that make our inequality true are the numbers in between -2 and 6, including -2 and 6. So now here's the thing. This is not your answer. The interval of x values that you write is your answer. So how do you say x can be any number in between -2 and 6, including -2, including 6? And I'm like 99% sure your homework asks for interval notation. So how do I say that? It would be -2 to 6, including -2 and 6. So we'd have to use brackets. So these are the x values that make this inequality true. Okay, so the sign analysis, it's not hard. It's literally just plugging and chugging numbers to see if they come out to be positive or negative. However, it's time consuming. It is time consuming. Now, if you have higher degree inequalities, you could end up with more numbers that make it equal 0, and then you there have even more intervals of x that you have to test. So with quadratics, it's pretty simple. If you wanted to use method 2, this is what you would have done. This was method 1. Let me show you method 2. And this is why I think right now, you're probably going to prefer method 2, because it's much quicker. All right, you still start the same. You still compare it to 0, but it already was compared to 0. You still find the zeros, so you still would have had 6 and -2. Throw them on a number line. Actually, throw them on a graph. -2 and 6. Now again, we want x values that make this a number less than or equal to 0. Since these numbers make it equal to 0, they're allowed to be answers. So you would put closed dots to remind yourself that they better be answers in some way, shape, or form. All right, now guys, use the graph of this parabola to tell you where the answers are. Guys, look at this parabola right here. A is positive. So would this parabola have opened up or opened down? Up. So give yourself a parabola that opens up. We know that's what it's looking like. Do I actually know the vertex? No, but I don't care. I know that a parabola opening up with these two x-intercepts would look something like that. I don't have to know how low it goes. I don't have to know where the vertex is. I just know in some way, shape, or form, that's what the graph of this parabola would look like. Now, guys, let the graph tell you where the good and bad answers are. We are looking for x values that turn this into a number that is less than or equal to 0. So guys, according to the graph, if I plug -3 in, what kind of number comes out? A positive number. So now you know that any number to the left of -2 creates a positive output. Guys, are positive numbers going to be less than or equal to 0? No. So this part of the graph tells you that they're not making the right kind of numbers come out. Therefore, that's not an interval of x values. That's going to be a solution to our inequality. Look here. According to this graph, if I plug any number in between -2 and 6 in, like if I plug -1 in, this number is coming out. If I plug 0 in, a number down here is coming out. If I plug 1, a number down here, 2, a number down here, 3, a number down here, and so on. If I plug any number in between -2 and 6, what kind of numbers come out of this function? A negative. Are negative numbers going to be less than or equal to 0? Yeah. So the graph is telling you that these are the x values that make a negative number come out. So those are good, guys. Those are solutions to our inequality. And then last, according to the graph, if you plug any number to the right of 6 in, like 7, 8, 100, whatever, what kind of number comes out of this function? Positive. A positive. Are positive numbers less than or equal to 0? No. So these are bad x values. They are not solutions to our inequality. And then without having to do any of this, you already know that the answers to this inequality are in between -2 and 6. So if you can whip up a really quick sketch of your parabola, whether it opens up or down, the graph tells you which x values make a negative or a positive number come out. So this is the method that I prefer when it's a quadratic inequality. If I can whip up a quick sketch of its graph, oh my God, so easy to find the solutions. So again, this proves it's -2 to 6. Are you guys okay? Everybody at home, are you okay? All right, I'm going to go to the next problem. I'm going to do it using probably method 2, and then I'll show you method 3, okay? Let me just get this out of the way. go too far. No, all right, here we go. Let's solve this one. So first, let's do it ourselves. Let's do it method 2. Let's get everything on one side compared to 0. Now notice, I just want to find x values that make this a number greater than 0, but not equal to 0. So now we should not be including our zeros because they're not equal to 0 in this problem. All right, I'm going to hope this factors. Let's find our zeros. Let's find those boundary numbers. All right, it factors very, very nicely. You gotta love when it factors. Set your factors equal to 0. And x could be 5 halves or negative 2. Everybody good with that so far? Everybody good? Okay. So guys, if you want, you can put these on an x-axis and then test a number in each section. I don't think you should have to do that with quadratics. The graph should be easy enough. So give yourself a quick sketch of a graph. Put your zeros. We got negative 2, and we got 2.5. We got 5 halves. All right? We said these are the numbers that make this expression equal 0. I just want to find x values that make this expression greater than 0. So don't include these numbers. So put open circles to remind you that you will not be including these numbers. Oh boy, I got kicked out.
So it's a weird reality check when you get kicked out.
I know. I'm like, wait, what just happened? Guys, I got kicked out. Is everybody okay? Can you guys hear me? I got kicked out of the meet on the one camera. All right, good. All right, so again, put those open circles to remind yourself that we're not including them. Now, guys, use a sketch of the parabola. It either opens up or down. If A is positive, is this parabola opening up or down? It's going up. So give yourself a parabola that would have opened up. It would have looked like that. Okay, let's look at what the graph says. According to this graph, if you plug a number to the left of negative 2 in, what kind of numbers are coming out of this function? Positive or negative? Positive. Are positive numbers going to be greater than 0? Yes. So these are good x values. X values over here make a positive number come out, and positive numbers will be greater than 0. Perfect. All right, according to the graph, if you plug a number in between negative 2 and 5 halves in, what kind of number do these x values make come out? A negative number. Will the negative numbers be greater than 0? No, these are bad x values. These will not make our inequality true. And then what about numbers to the right of 5 halves, to the right of 2.5? Any number to the right of 2.5 makes what kind of number come out of this function? Positive. Are positive numbers greater than 0? Definitely. These are good x values. So again, this isn't our answer. The intervals of x that you write are our answer. So how can we say x can be any number to the left of negative 2? What is this interval of x values? It comes from negative infinity to negative 2. Right? And again, use a parenthesis because we do not want to include negative 2. And then we can union it with what's the next interval of x values that make it true. These were bad, these were good. So what kind of x values live here? X is from 5 halves to infinity. But don't include 5 halves, and we never include the infinities. Now, I'm just going to be honest, I'm not 100% sure whether the online homework asks you to put a union or a comma. So just read the direction box under it. It'll tell you to list intervals using a comma. If it doesn't say use a comma, then you know to use the union. Go ahead.
I think typically it makes you put the union.
I think so too, but for some reason, sometimes with these intervals, they let you list them as commas.
Just so that's all kind of one.
Right.
It's not like, oh, this is one, and then this is
right. But I wasn't sure, so I want to warn you guys to pay attention to that. All right? So guys, like I said, if you use the graph, I feel like these could be really, really quick problems. Let me show you what this whole third method is. The third method is to use the intersection of the graphs. So you would treat 2x squared as one function, and you would treat x plus 2 as another function, and you would see where the graphs intersect. Now, we already know where they intersect, so we found where they're compared to. So Desmos, to me, is a really nice user-friendly way to see this instead of the graphing calculator, just because it's so much prettier. So you would treat 2x squared as one function and x plus 10 as another. And now you would be looking for, what did it say originally? It wanted 2x squared to be greater than x plus 10? Is that what the original problem said? So now you would be looking, where is the parabola, the red graph, above, greater than the blue graph, the line? It's greater than it from an x value of -2 all the way to infinity. All of these, this part of the graph is where it's bigger. So from -2 to -infinity. And then it meets here at 2.5. And see how the parabola, the red graph, is above the blue graph from 2.5 all the way to infinity. So again, so it does show you can use the graph and then compare where one graph is above the other graph and on what x values it happens on. I don't think it's necessary with a parabola because the parabola sketch is pretty quick, okay? All right, let's see if we can do example 3. All right, so again, I usually just show you guys using the graph. All right, let's do this one. Let's compare it to 0. So let's add that 25 over. All right, we compared it to 0. Let's find the 0. So let's hope it factors.
What do you do in cases where you have to use the quadratic formula?
That's the next example.
Oh, you get like a really cruddy number.
Yeah, but it actually, you'll see. It doesn't happen every time, but just to make you aware of it. All right, so guys, you actually find out that only x equals 5 is your 0. So remember, they want x's that are going to make this expression greater than or equal to 0. Since 5 is the number that makes it equal to 0, make sure you include that, okay? All right, so give yourself a graph. Here's 5. And we want to make sure we include them. Well, guys, does this parabola open up or down? Leading coefficient is positive, it's opening up. So that means it was basically tangent to the x-axis at its 0. All right, so guys, let's play the field, right? We only have 2 sections. We have to the left of 5 or we have to the right of 5. According to the graph, if you plug a number to the left of 5 in, what kind of numbers come out of this function or this expression? To the left of 5, what kind of numbers come out?
Positive.
Positive. Are positive numbers greater than or equal to 0? Yeah, these are good guys. All right, and what if you plug a number to the right of 5 in? If you plug a number to the right of 5, what kind of values come out of this expression or function? Positive. Are positive numbers greater than or equal to 0? Yeah. So guys, look, these numbers were good, 5 was good, and all of those numbers are good. What are your solutions? What numbers make this inequality true?
Negative.
All real numbers. Negative infinity to positive infinity. All right, let's play a game with this one. Let's pretend that it just said greater than 0. If they just wanted this to be greater than 0, would 5 have been an answer?
No.
No. So you would have had an open circle. These still would have been answers. They still make it greater than 0. And these still would have been answers. They still make it greater than 0. So then the only number that wouldn't have been an answer is 5 himself. So then it would have been negative infinity to 5, union 5 to infinity, okay? All right, let's pretend it said this. What if it said less than or equal to 0? Well, then 5 would have been an answer, but do any numbers besides 5 make this less than or equal to 0? No, so the only answer would have been 5 himself. All right, and then again, I think you just put 5 like this, if just 5 is the answer. Or it might just be the set of x values, x equals 5. Maybe just let you write x equals 5. All right, and then if it had just said less than 0, 5 would have made it equal 0, but do any numbers make it less than 0? That would have been a no solution, okay? All right, perfect. Let's see if we can squeeze one more in and then go from there. Actually, I have 3 minutes left. Is that true? Okay. But I don't want to start the next one because it's going to cut me off. Okay, so what I'm going to have to do is the last 2 examples were just to kind of show you a couple other scenarios. The next one, example 4, it doesn't factor. You have to use the quadratic formula. So I'll fill that in on our notes, and you'll be able to see what happened in that problem.